In this session, we're going to review some things that are basic to time series modeling. I just want to reinforce some ideas. And I also want to give you a little bit of a preview of some more tools that we will be introducing. In particular, one of those tools is something called the autocorrelation function. Here are some things that are fundamental. Plot the data, plot the errors, look for anomalies. Look at something called the autocorrelation function of the data itself. Look at the autocorrelation function of the errors. As an example, this is the Dow Jones data that we worked with in class. Does the random walk model fit the Dow Jones Industrial Average? Well, yes, except when it doesn't. The chart shows that all the points fell within the predicted range of variation, except for one point that doesn't obey the rules of the random walk. And we have an explanation for that. That was Brexit. So we start to understand how to state the assumptions that go with our forecast. Those assumptions would be something like, it works pretty well, but it can't anticipate surprising economic news. And one thing that we learned from this, that it's always a good idea to chart the actual versus the forecast and the predicted range of variation. This slide shows that it's also wise to plot the errors, sometimes called the residuals. As we will learn later, if we have the optimal forecasting model, the errors should look like noise or independent, identically distributed random variables. I should qualify that by saying any deviation from randomness should have an explanation, such as the Brexit vote. This chart shows the residuals, and there's another anomaly there. In addition to the Brexit vote, there were 9 positive residuals in a row. And that is very unlikely to happen due to chance. The reason for the 9 points in a row are more subtle. It has to do with some positive economic news that came out during July, I believe. The other warning I want to make is to not read too much into patterns that you think you see, but are not really low probability events. For example, an error, 2 standard errors from the center line, happens about 1 time in 20. A run of 4 or 5 or even 6 will happen once in a while. So we need to have some rules that say these things are events that would be very, very unlikely to happen in a sequence of random data. Now let's switch to the fasteners data. We're going to talk about something that we haven't discussed much yet, and we will take up later in the course, and that is the autocorrelation function. With the data that you had with fasteners, you had the actual monthly sales and a forecast that the company was already compiling. One of the things that you may have done is to compute the correlation of the error with the error of the previous month. That is called the lag 1 autocorrelation, and you found it to be positive. Now let's think about that for a minute. If over forecasting this month means you're also going to over forecast next month, or if under forecasting this month means you're going to under forecast next month, why wouldn't you use that knowledge to improve your forecast? You can compute the autocorrelation for each month with the error 2 months earlier, 3 months earlier, 4 months, and so forth. These are called the lag 1, 2, 3, 4, etc. autocorrelations. And if these are not for all practical purposes 0, it says that you can improve your forecast. And this particular autocorrelation function for the errors of the fasteners data, the autocorrelation spikes at months 3, 6, or lags 3, 6, and 9, and 12. Which says that the errors have a seasonal pattern in them. And if you had plotted the errors, you would probably have already seen this. If we plot the demand data itself for the fasteners project, we see that there's a pattern that repeats every quarter. Now, when we investigate, we find that this is the way the data is organized. There are 13 weeks in a quarter, so the first 2 months of each quarter have 4 weeks, and the third month has 5 weeks. So our reaction is, oh, we can fix that. We'll convert each month to a weekly rate by dividing monthly sales by the number of weeks in that month. Once we scale the data of each month to a weekly sales rate, we get this. And the data still has a pattern in it, particularly sales spike in January of each year. And we are going to have to talk to the people that provided this data, the people we're working with, and learn why that happens. And that also tells us if we model this data, we're probably going to have to build that seasonal pattern into our model in some way. So in summary, what these few slides point to is time series modeling requires a strong sense of intellectual curiosity. You need to want to learn how things work rather than just take the numbers as given and attempt to do the math on them without understanding the underlying process itself. So it requires you to have a willingness to learn a lot about the subject matter that you're modeling. It also requires that you do a lot of what I would just call playing around with the data, plotting it, looking at the autocorrelation function, looking for outliers, and getting as familiar with the data as you possibly can. So time series modeling, the math is rather simple, but that has to be combined with a lot of good common sense.